Hey folks, let's pick up where we left off here. We were looking at domain and range and symmetry. In this case, it looks like they're only asking for domain initially. So domain is always found the same way. What do? What 3 words? Look for problems. See if we have any problems here, and I think we have 2 kinds of problems. We have a problem here because we're trying to natural log something. So anything inside of a natural log must be positive. You cannot log a non-positive. So this stuff, x plus 3, must be greater than 0, not greater than or equal to. That's the one with the even roots. So if we solve that, we know that x must be greater than -3. We also have a problem in the denominator, and what I call a double problem. We have an x on the bottom and an x underneath a root. So that means that this stuff cannot be negative, nor can it be equal. This stuff has to be greater than or equal to 0, but it also can't be equal to 0. So we can combine those and just say that whatever this is, it must be greater than 0. It can't be equal to 0, and it can't be negative because it can't be equal to 0 because it's on the bottom. And then we would get a 0 on the bottom, which is bad news. And we can't get anything negative in here because we can't square root a negative. And as I start to solve this, I get x squared is greater than -4, and I realize, oops, this isn't a problem after all. Oops, I don't know how to spell oops apparently. Oops. If you square root both sides, you'd get an imaginary, so we don't have to worry about that. So this isn't a problem. After all, because we tried to solve it and we weren't able to. So what would our domain be? We just said that we do still have this restriction that x has to be greater than -3. So let's bring that down here. Our domain. Okay, so x has to be greater than -3. That means we can start at -3 and then go off to infinity. Let's do a quick test for symmetry. If I plug a negative x into this, -x plus 3, this is not going to be solvable. So when I put my negative x in there, it's going to take my function, it's going to reflect it, but we know our log graph is not going to have any nice symmetries. So, I mean, we can probably just guess. If we wanted to sketch it, if you looked at the picture, here's what the graph would look something like. And that clearly doesn't have any rotational symmetry around the origin or reflective symmetry about the y-axis. A couple of notes in there. Oh, shoot, I should have written this down. A test for symmetry. What do we do to test for symmetry? Plug in -x for x and see what happens. Okay, so he talks in here, and he likes to kind of put the highlights of this problem in this little box here. And he first starts off talking about just because you have an even radical doesn't automatically mean you're going to have a problem. We just have to check to see if it's a problem. It doesn't mean it has to be a problem. When we're talking about the domain of a log function, so how do I want to say that? Just because a function has a radical doesn't mean we'll have a domain restriction. It doesn't have to be true. We also can only take the log. The log functions must be greater than 0. So when we set up our inequalities, what can and can't be, we got to set that equal to 0. And then just a quick review of, set that greater than 0, sorry. And then just a quick review of our interval notation. Less thans and greater thans are included, so we would use the bracket. Sorry, less than or equal to, or greater than or equal to, I said that wrong. Less than or equal to, greater than or equal to are included. Less than, greater than are not included, and we indicate that with a parentheses. And when you're writing something in interval notation, you must always list from least to greatest. So we never write like infinity, comma, -2, because -2 is smaller than infinity. In interval notation, the infinities always get parentheses. Remember, we can never include those. If you're interested, the infinity symbol is called a lemon skate. I can help you graph that if you're interested using polar coordinates. You might remember that from the homework from the spring in pre-calculus. We went over polar graphs. And the graph of x has a root argument here at x equals 3. Notice again how the calculator, so this is him just highlighting again, and I think it's worthwhile. Notice how the calculator stops abruptly. Even though it really shouldn't, your calculator stops because this graph gets too vertical. So sometimes it's easier to look at your calculator to get an idea and then make a sketch from there. And how do you know when it stops or when it doesn't stop? Well, that's because you know about families of functions. For the most part, what do we know about natural log, right? This is this graph that this looks like a natural log graph. So this function that's a division involving natural log is going to have a lot of the characteristics of the natural log graph. Find the domain and justify symmetry. Here we go again. How do you find the domain? We've done it a lot. You should look for problems. So we do have a problem here, right? This would be a problem if negative x must be greater than or equal to 0. When I divide both sides by a negative, I get x is less than or equal to 0, which turns out to be exactly the range and the interval in which they define our function. So we don't have that. Kind of looked like it was going to be a problem, but because all of the x's that we're choosing are already negative or 0, when I plug them into this, they're going to come out to be positive. So actually, that isn't a problem after all. Natural log of x plus 1, that is a problem. We can only log positives. So x plus 1 must be greater than 0. If I solve that, x must be greater than negative 1. So this is a piecewise function, and we have to now check to make sure that the moment when they transition from the first curve to the second curve is actually included, and there is a point included there. So when x equals 0, so that is going to be part of our domain. What I mean by that, let's say this was x is less than 0, and this was x is greater than 0. That means that our function is not defined at 0, which means that we don't have 0 in our domain, which means we'd have to take that into account as a problem as we go through. Just a reminder of how piecewise functions work. This part, this piece, y equals negative x, corresponds to everything to the left of and including x equals 0. So this graph occurs for all the x's that occur before 0 and including 0. And then our other part, our other piece, are all the things that occur to the right of 0. When you're doing a piecewise graph, you should make sure you figure out that every single point is defined. That's what I did when I looked at what's happening at 0 itself. And then you would look at each individual graph. So like in this one, we have a problem here at x equals greater than negative 1. But what's our domain, or what's our function? What's that piece of the function defined as? It's already defined to be greater than 0. So this turns out to be not a problem because I don't know what do you call these parts? Does he say what they are down here? And because only defined for x is less than or equal to 0. So we're already in good shape. What that means is the only things that would cause us a problem don't already fit into the interval that we're looking. So everywhere we look, things are good. Same thing down here. Our problem occurs for anything that is not greater than negative 1. But if you're greater than 0, you're automatically already greater than negative 1. Not a problem either. It started off as a problem, but it turned out to not be that. It didn't turn out to have much of an effect. So as we look at our picture, it kind of feels like there's some symmetry here. If you were just to sketch this, you might sketch it like this. But if you'll notice, pay a little bit closer attention, you could see that these two branches don't actually meet each other. Sorry, I should say that they do meet each other, but they don't reflect over the y-axis. They're not exactly the same across the y. We don't have any problems, so our domain, we can highlight, they wrote it already for us. Our domain, all real numbers, negative infinity to infinity. You got to be careful here. Notice that the two pieces seem to meet at the origin, and in fact, they do. They do meet there, but we're not reflective. We don't have any symmetry across there, but not symmetrical. So even though they meet, they have some sort of characteristics of an odd function, they actually don't. Now, and then down here, he actually writes it up. I want to leave a note that saying I would never do something this sneaky. I would never give a problem this sneaky. And neither would College Board. What I mean by that, if they let you use your calculator, then you would look at this. I would never give you one that was that close to being that close to being symmetrical across the y-axis. And College Board wouldn't either. If you couldn't use your calculator, you could, well, this is where it starts to get a little nasty. I mean, you could just probably look at this and knew they wouldn't be symmetrical. I mean, does the graph of log look like the graph of square root? I hope you would say no. Those are two very different graphs, so we should know that they're not going to be symmetrical. But they wouldn't give you one that on your calculator that when you graphed it, it would look this close. And that's what he's talking about here, the relative growth rates. If I were comparing of each of the two functions, so a square root function versus a log function, these two functions grow very differently from each other. So that's another reason why they're not symmetrical. All right, here's our last example for P5. We've got another piecewise function. So let's have you start off and figure out the domain. Domain should be fairly easy. Try not to look down too far. And try to figure out if you can see where the domain is. All right, hopefully you pause it. If you haven't paused it, you should pause it right now. So as I look at this first piece, yeah, we have a problem. Because we've got a z on the bottom. So z plus 3 cannot be 0. Therefore, z cannot be negative 3. Is that a problem in our domain? Yes, it is. Like before, remember, all of our problems didn't end up being in the intervals in which the function was defined. This time it is. Z is less than negative 2. Negative 3, it belongs in that group. So we're going to have to keep track of this one. Let's look at the next piece. Do we have any problems there? Nope, life is good. No problem there. Look at the last piece. Life is good. No problem here. Now, because this is a piecewise function, we should look at one other place. We should look at all the transitions between one piece and the next and make sure that they're defined. So what I mean by that is if I circle, okay, z at negative 2 is not defined here, but is defined here. So it is included. That is included. Now let's look what's happening at 2. When I look at 2, Sorry about that. Swanee had to tell me a joke. So if I look at what's happening around 2, what would be a good color here? Maybe purple. This is a problem. Even though it doesn't look like it, this is a problem because this is not included. So Z cannot be 2 in our interval. Okay, let's see how it went. This is a 3-piece function. Most interesting values are -2 and 2. You see what he's talking about there? That's the way these are defined, right? That's the transitions between the pieces. We also noticed that there was a problem at Z equals -3, which he also mentions. I'm going to highlight some of this stuff. Our interesting values are the transitions. We found one of them worked and one of them did not. The other interesting piece is that our function is not defined. So, sorry. The function is not defined at Z equals 2. So Z equals 2 is not in our domain. And then because of our rational function here, we could say that Z cannot be -3, something we already talked about. So what would our domain be? So let's try to write our domain in this little spot here. If you haven't paused yet, you should try it. All right, well, if you can't include -3 and 2, it's a pretty easy domain to write up. We go from negative infinity to -3, union, -3 to 2, union, 2 to infinity. So now we've included everything except for -3 and +2. So the rest of this, he kind of just talks about how to put this into your calculator. So if you'll notice, if you want to do a piecewise into your calculator, you can. You just put parentheses around what's called the argument. I think that's what that's called. So let's see how this is. So we did 1 over x plus 3. That's our function. Divided by, and then the quantity, x is less than -2. Our next section is x squared minus 2. Divided by the quantity, x is greater than -2 and x is less than 2. And then 2 to the x for all x that are greater than 2. And then your calculator would actually show it this way. If you wanted to practice, you could grab your calc. This is what your picture should look like if you use this window. A couple of things to talk about. You must include the union symbol. So you need to use the union symbol in between your intervals. To graph a piecewise function, that's what I was just talking about here. To graph piecewise on your calculator, enter each piece and then divide it by a Boolean argument. That means the and or stuff. And then a nice trick is the zoom decimal. I just found out about this one. Zoom decimal, when you hit zoom decimal, you can actually see holes in your function. I want to show you this one because I think it's so interesting. So I'm going to graph a curve. Let's make it something that definitely has a hole in it. So I'll go alpha F1. And then I'll pick my first function to be x, or the numerator to be x plus 1, x minus 2. And then in the denominator, I'll have x plus 1, x plus, let's go x plus 2. Is this going to have a hole? Hopefully your math voice is yelling, yes, because x plus 1 and x plus 1 will cancel out. So we should have a hole at -1. If I just hit graph, or if I do what we normally do, which is zoom and then hit 6, go down to zoom standard, the standard window, there's our picture. All right, not too bad. But if I do this one, zoom and then decimal, when I hit enter, where was our hole? Oh, this is actually kind of a crummy window for it. Oh, crap. Of course, right during the video. Where was that hole at? -1, wasn't it? Zoom, decimal. Ah, darn it. I was hoping it would show it a lot nicer than this. What if I change these to pluses? Or minuses, I mean. Sorry. Zoom, decimal. There it is. You see it? That one's a little bit better. Hopefully you can see that one a little bit better. I don't know why the other one didn't work as well. See how it actually took out the hole at when I traced to 1? Traced to 1, there's no value there. So anyway, kind of interesting. I don't know how much it'll show up, but something worth remembering. What else do we have? When sketching a graph by hand, yeah, remember when we sketch by hand. So now that we actually are trying to draw this thing, we want to put a solid dot or an open circle on the endpoints of the interval to decide whether they should be included or not included. Remember how that works? The solid dot, excuse me, solid dot goes with inclusive, open circle goes with not inclusive. Solid dot is inclusive, open circle means not included. All right, so that's it for the notes. Give the homework a try. Good luck.